Hey everyone, we are moving to chapter 17 for the next couple weeks. This is, I'm hoping, going to be a fun chapter for you guys. It's all about electrochemistry. Now, electrochemistry itself is a really challenging concept and wing of chemistry. We're not going terribly deep into it, so don't stress yourselves out too much. This chapter is more of a theory chapter. There is some stuff that you have to be able to write and stuff, but there's going to be a lot of explaining and examples. I'm hoping, I think and hope you're really going to like the last couple sections of the chapter. There are 6 sections to this chapter, but they're all relatively short. So we're going to start by reviewing redox chemistry, and then talk about galvanic cells, electrode and cell potentials, potential, free energy, and equilibrium, batteries and fuel cells, corrosion, and electrolysis. So this all relates to things like rechargeable plug-in electric and hybrid cars. They have batteries that can be recharged, so they're using electric energy, which brings about a chemical change, and vice versa. We'll talk a little bit more about these in section 6. So in our first section, we are going to do a brief review of redox chemistry. So hopefully you remember this from Chem 2A, redox reactions and balancing redox reactions. If you don't, I highly recommend that you go back over those. The YouTube channel, I have a playlist for Chem 2A, and there are my videos from last semester that I'm using this semester also going over redox chemistry. So I highly recommend that. Goes over balancing redox equations as well. So in this section, we're going to describe the defining traits of redox chemistry, identify the oxidant and reductant of a redox reaction, and balance chemical equations for redox reactions using the half reaction method. So let's start by defining electrochemistry. This is the study of the interconversion of electrical and chemical energy. So these chemical reactions involve electron transfer. Electricity is the presence and flow of electrical charge. And electrons themselves, or ions, may be what is actually carrying the charge. So if you remember from redox chemistry, we have oxidation and reduction. Oxidation, which involves the loss of electrons, so electrons are produced and the species is oxidized. Reduction occurs when you have a gain of electrons, so electrons are consumed and the species is reduced. So do you remember the saying, oil rig? Oxidation is loss, reduction is gain. There's also Leo the lion goes grr. Loss of electrons is oxidation, gain of electrons is reduction. And if you remember, when it comes to redox reactions, that's what we call these, oxidation reduction or redox reactions, both oxidation and reduction are occurring simultaneously. So it's not one then the other, these are happening at the same time. We also introduced these concepts of the oxidizing and reducing agents. So what the species that causes the other species to be reduced is the reducing agent or the reductant. And something that causes the other species to be oxidized is the oxidizing agent or oxidant. So the oxidizing agent is reduced, the reducing agent is oxidized, and both of these end up being reactants in the overall redox reaction. So this is one thing that's really important to remember. The oxidizing and reducing agents are reactants in our overall redox reaction. They are not products. And you have to have both in a redox reaction. You can't just have something be oxidized and nothing be reduced. There's a balance. We had also learned about oxidation numbers, which let us determine what is being oxidized and what is being reduced. If you have an element or a monoatomic ion, the oxidation numbers are just the charge of that species. And then if you have a molecule or a polyatomic ion, the oxidation numbers really are not real charges, and there are rules for assigning oxidation numbers, and you can go back and look at those rules to review. So these are generally small whole numbers, but they can be fractional. There's the occasion where you can have a fractional oxidation number. Generally, we don't deal with that here. So oxidation results in an increase in oxidation number. For instance, copper solid, this has an oxidation number of 0 since it's an elemental form, and it is going to copper 2 plus and 2 electrons. Okay, so it's oxidized, it's losing electrons, but its oxidation number goes from 0 to plus 2. So its oxidation number goes up. Reduction results in a decrease in the oxidation number. So it's a reduction in oxidation number. For instance, we have 2 silver plus ions and 2 electrons becoming 2 solid silver, so that has a charge of 0. So we're going from a charge of plus 1, increasing an oxidation number to a charge of 0. And we had also learned about balancing redox reactions. Your first step is to assign oxidation numbers to everything in your reaction. Split the reaction into 2 half reactions, the one that is the oxidation reaction and the other that is the reduction reaction. And you want to balance each half reaction separately, and there's special ways to balance them. You start by balancing everything except hydrogen and oxygen. So we say everything except hydrogen and oxygen. And then the next step is to balance oxygen by adding H2O to whatever side or sides need it. And then lastly, you balance hydrogen by adding H+. And you do this for each half reaction. And then you need to take those 2 balanced half reactions in such a way that you eliminate the electrons. Oh yeah, and then I forget, then you need to add electrons to balance charge on each side. Add that first over here. Balance charge. And if you need to, you multiply one of those half reactions by an integer so that you have equal amounts of electrons in each half reaction. Combine your half reactions, eliminates your electrons, and then make sure everything is balanced. If you are in a basic solution, then you need to add hydroxide ions into the equation to neutralize the protons. So you added in equal sides to the reaction, and then you take the OH minus and the H plus, combine them to make water. And then you make sure at the end that any redundant species on both sides of the reaction arrow are canceled out. And we're going to look at an example going through our steps to refresh your memories. Alright, so here's our first example to refresh our memories on balancing equations for redox reactions. So this one we want to write the balanced equation representing the reaction between solid copper and nitric acid to yield aqueous copper 2 ions and nitrogen monoxide gas. So we can start by just kind of writing a rough overall reaction. We know we have solid copper and nitric acid. That's the acid, it's going to be aqueous, giving us copper 2 ions and nitrogen monoxide gas. So we can go ahead and assign some formal charges here to what we already don't know. So we know copper 2 plus, that's already 2 plus, but copper, the solid copper, is going to be 0 since that's in its atomic elemental form. And then if we go over to, for instance, NO, the oxygen generally has a charge of -2, so the nitrogen here is going to be +2. For HNO3, we can think of this as hydrogen bonded to NO3 minus. So hydrogen is +1. Each oxygen tends to be -2, so that means we have -6 in total from all the oxygen. So then we need this whole molecule to be neutral, so that means that this nitrogen has to be a positive 5. So looking at this, we can see that the copper is oxidized in that it goes up in oxidation number from 0 to positive 2. And the nitrogen is reduced in that it has a reduction, or it reduces in its oxidation number from +5 to +2. So now we have our oxidation and our reduction sides. So we now have written our half reactions identifying the two sides of the reaction. So the first step is or the second step, I guess, is to balance each half reaction for everything except hydrogen and oxygen. We're already done. Let's go ahead and change my pen color for the different steps. Okay. Now, the next step is to balance each reaction for oxygen by adding water. So the copper side, there's no oxygen to balance, but on the nitric acid side, we do need to balance oxygen. We have 3 oxygens on the left, whereas only 1 on the right. So we need to go ahead and add 2 waters to the right side. Our next step is now to balance our hydrogen by adding H+. So our copper side is already balanced, there's no hydrogen to balance, but on our nitrogen side, we have 4 hydrogens on the product side versus 1 hydrogen on the reactant side. So we need to add 3 more hydrogens. So but this time it's going to go to the reactant side. So now we have 4 hydrogens on each side. Now we need to go ahead and balance each half reaction for charge by adding electrons. So now we're going to have to do something to each side. So on the oxidation side with the copper, we have a charge of 0 overall on the left and positive 2 on the right. So to balance this for charge, we need to add 2 electrons to the right side, because that's adding -2. So you have -2 plus the positive 2 from the copper. That gives you overall 0. On the reduction side, the nitric acid side of the reaction has an overall charge of +3 due to those 3 hydrogen. And the NO side has an overall charge of 0. There's nothing there giving charge. So then to balance, we need to go ahead and add 3 electrons to the nitrogen side. So now we have the -3 to balance out the +3. The next part is to multiply one or both reactions by a number so that we can have the same number of electrons that are going to be consumed. Notice one of them has the electrons on the right, the other has them on the left. Now, when you have something like one number has a 2 and the other has a 3, crisscross them. So the one that has 2, multiply it by 3. The one that has 3, multiply it by 2, because then you get 6, your common denominator. So we're going to multiply the copper side by 3 and the nitrogen side by 2. And we can rewrite these half reactions. So we have 3 coppers going to 3 copper 2 plus 6 electrons versus 2 HNO3 plus 6 H plus 6 E minus going to 2 NO plus 4 waters. Okay, now our next step is to take these 2 half reactions and put them together. So I'm going to first erase this line down the middle and redraw it. So we need to combine everything. Let's go ahead and use dark red. What I like to do is I like to draw my 2 arrows for my half reactions and have the arrows lining up for adding them together. Not everyone likes to put them on top of each other. It's really up to you how you want to do it, but I'm very visual. So I do it this way so that I know what goes where. So I'm just rewriting. I'm writing my product side first. I don't know why, I just am. Okay, and then we had over here. Okay. So now we've written our half reactions. This is when I start canceling things out. You could always write the overall reaction and then cancel things out, but I like to do it kind of like a system of equations. So I look at this and I see 6 electrons on the left versus 6 on the right of the arrow, so those are going to cancel out. And that right now is the only thing that cancels, which is good. The electrons are supposed to cancel. We don't have water on either side to eliminate, so now our final answer is just combining everything. So we have 3 copper, 2 nitric acids, 6 protons, combining to form 3 copper 2 plus 2 NO plus 4 waters. And that is our final answer there. So that ends this example. You can go through and you would see that we have the same charges on both sides. On the left side of the equation, we have 6 H pluses, which gives us a +6. It's the only place we're getting charge, whereas on the right side, we have 3 copper 2 pluses, which is +6. So we are charge balanced. The numbers of each element are balanced on each side as well. So that is balancing in acidic solutions. The next example is balancing in basic solutions. So we want to write the balanced equation representing the reaction between aqueous permanganate ion and solid chromium 3 hydroxide to yield solid manganese 4 oxide and aqueous chromate ion. And we're told this is in basic solution. So one thing to remember is if you are in acidic solution with a redox reaction, there cannot be any OH minus. If you are in basic solution, there cannot be any H plus. Okay, you can have OH minus in basic solutions, but you can't have H plus, and vice versa for acidic. So we are looking at MnO4 minus and CrOH3 taking MnO2 and CrO4 2 minus. Okay. So you can always go and look at oxidation numbers and stuff, but we can also go ahead and just divide this up into our half reactions. Even if you can't necessarily tell what's being oxidized versus what's being reduced, sometimes writing the half reactions ends up helping you. So for instance, I go, all right, I see chromium, so there's definitely something going on with chromium. CrOH3 going to CrO4 2 minus versus manganese seems to be the other one, MnO4 minus going to MnO2. So we already know what our half reactions are, even without going, oh, this is oxidized, this is reduced. So it's just something that I've always just kind of done for myself, instead of getting myself hung up on, oh, what's oxidized, what's reduced. It's okay to sit back and go, oh, I see. We can look at this though, with like the chromium 3 hydroxide. We already know chromium's charge from it telling us the name. It's 3 plus. And then we have this chromate ion. So it has an overall -2 charge. We have 4 oxygens, so that would be -2 each oxygen. That's -8. But then we need this to be -2 overall, so you can add 2 to that if you will. So -6 that we need to balance out. So that means this chromium here has to be 6 plus. So this is increasing in oxidation number. So that's our oxidation side. Looking at the manganese side, we know that the manganese is +4 on the product side because it told us manganese 4 oxide. And then if we look at the reactant side, we have MnO4 minus. So that means we have a -1 charge overall. We have 4 oxygens, so that's going to be -8. We have 1 oxygen, or 1 that's being neutralized by a positive charge, so then -7. So that means this manganese has to be a +7. So it's being reduced because it's having a reduction in its oxidation number. So now let's go ahead and go through our steps. First is to balance things that aren't oxygen or hydrogen. Those are already balanced, so we got off the hook there. The next is to balance oxygen by adding water. So on our chromium side, we need to go ahead and add a water because we only have 3 oxygen on the left versus 4 on the right. And then for the manganese side, we have 4 oxygen on the left versus 2 on the right, so we need to add 2 to the right side. And just remember that water is the liquid phase. Now the next part is to balance the hydrogen by adding H+. So let's see, let's start with the chromium side. We have 3, 4, 5 hydrogen. So then we need to add 5 to the right side. And then for our manganese friend, we have 4 hydrogens on the right, which means we need 4 on the left. And then we need to go ahead and balance our charge by adding electrons. So we have on the chromium side, 0 on the left, and then -2 plus 4 gives us +4, so we need to add 3 electrons. Or I'm sorry, -2 plus 5 is -3, or +3. Wow. I'm great with numbers right now, aren't I, guys? So then that gives us 0 on both sides of that equation. For the manganese side, we have -1 plus 4 gives us +3 on the left and 0 on the right. So we need to add 3 electrons on the left side. So then this time we have 0 charge on both sides. And we see that both of them have the same number of electrons that are being added. So we're good there. We don't need to multiply by a number. So now let's go ahead and change pen color and combine our 2 half reactions. I'll use black here. So we have CrOH3 going to CrO4 minus, oops, H2O plus. It's 5H plus 3 electrons. In our other reaction, we have MnO4 minus plus 4H plus aqueous plus 3 electrons going to MnO2 solid plus 2 waters. And now we can go ahead and cancel things out. So a couple things that we can see here is we can get rid of this water because we have 2 waters on the right side, so that just takes this 2 down to a 1. We see the electrons canceling. We also see these 4H plus on the left going away and bringing down the 5H plus down to 1. Okay, so that's looking like just about everything. So let's go ahead and write what we have right now. So that leaves us, at the moment, we have CrOH3 plus MnO4 minus going to CrO4 plus H plus MnO2 solid plus water liquid. But we are not done yet. This is a basic solution, and like I said at the beginning, you cannot have H plus in a basic solution. So we need to go ahead and balance the H plus by adding OH minus to both sides of the equation. So this is kind of like in algebra. You add one to one side. That means you have to add one to the other because technically they would cancel out. So we add OH minus, add as many as you need to cancel out those H pluses. In this case, we just need one. But that goes to both sides. And then when you have an H and an OH, that makes a water. And then I have now two waters to rewrite. So now rewriting our overall reaction, we have CrOH3 plus MnO4 minus plus OH minus, we just added that, gives us CrO4 2 plus MnO2 solid plus 2 waters, since we added those two together. And that is going to be our final reaction balanced in basic solution.